Do you know the efficiency of the motorcycle what you are using is well below 50%. If the efficiency becomes 100%, then the average of your motorcycle will be almost doubled. But here the question is that can we get 100% efficiency ever? Want to know the answer? Then get engaged with this lecture today. Welcome all of my dear students. Let us see a wonderful topic today, and the topic is 12.11, second law of thermodynamics. The first law of thermodynamics is basically the principle of conservation of energy. Yes, this you know already. That the first law of thermodynamics is explained on the basis of conservation of energy only. Right. That means internal energy also obeys the law of conservation of energy as mechanical energy and other energies do. Because in first law we have understood the internal energy, and the first law is obeying conservation of energy. So obviously the internal energy would also be obeying the law of conservation of energy as mechanical energy and other energies are already doing. But still we have never seen any example where internal energy spontaneously gets converted into equal amount of mechanical energy. Means we never see that internal energy of any object is converted into equal amount of mechanical energy, that too spontaneously. Have you ever seen such type of example? See, your room is full of gas molecules, and the total amount of energy of this gas molecules is the internal energy, right? So is it possible that the total internal energy of the room is converted into, let us say, electrical energy, or let us say mechanical energy, or let us say kinetic energy? Have you seen any such type of example? No, never. Now here is the question: what is wrong if internal energy is converted into same amount of mechanical energy? Nothing wrong, because as per the conservation of energy, the same amount of internal energy can be converted into the same amount of mechanical energy. Nothing wrong there. But still we don't find this type of case ever. Now this shows that some basic principle of nature forbids this to happen. That principle is nothing but the second law of thermodynamics. Means the natural phenomena, or say the basic principle due to which internal energy is not being converted into mechanical energy spontaneously, is the second law of thermodynamics. Let me explain you this with one figure here. See, here is a bowl filled with some water, right? And here is a stirrer, and we are rotating the stirrer. So we are doing some work. That means we are spending some energy. Let us say we have spent some X amount of energy. Alright. Now we know that due to the motion of this stirrer, the temperature of water will rise. Here in this second figure you can see that the temperature is increased. That means the internal energy of water has been increased. Now the increase of internal energy will be equal to the work done in the first figure, or say the mechanical energy spent in the first figure. That means in the first figure, if the mechanical energy is X, then here in the second figure the increase of internal energy will be also X. Now the question is that the increased internal energy gets converted into mechanical energy again spontaneously. Is it possible? The answer is strictly no. Why? Because of second law of thermodynamics. This law gives fundamental limitation to the efficiency of heat engine, not allowing it to be 100%. And the same way, limitation to the coefficient of performance, not allowing it to be infinite. See, the second law is the law which is not allowing the efficiency to become 100% in heat engine, and the same thing is happening that the coefficient of performance is not becoming infinite in heat pump or refrigerator. So the conclusion is, if the second law of thermodynamics won't be there, then our motorcycle would be giving 100% efficiency. But because the second law of thermodynamics is present everywhere, so we are not getting 100% efficiency in our motorcycles. Now let us see the statements summarizing the second law of thermodynamics. Now let me tell you here that there is no particular statement for second law of thermodynamics. Basically, two statements, Kelvin-Planck statement and Clausius statements, are the statements which represents the second law of thermodynamics. So let us see first Kelvin-Planck statement. By this statement, they, means Kelvin and Planck, denied the possibility of perfect heat engine. They said that no process is possible whose sole result is the absorption of heat from a reservoir and the complete conversion of the heat into work. Means they said that it is not possible to convert 100% heat into 100% work. And the second statement, that is Clausius statement, is below. Here he denied the possibility of a perfect refrigerator or a perfect heat pump. The statement was, no process is possible whose sole result is the transfer of heat from a colder object to a hotter object. Means it is not possible that the heat will transfer from colder object to hotter object without doing any work. Alright. Now here these two figures represents both the statements. The first figure represents Kelvin-Planck statement. Here you can see that this is hot reservoir at temperature Th and this is cold reservoir at temperature Tc. Here the heat Q is being converted into work W. There is no loss of heat, that means 100% heat is converted into 100% work. That means this will become a 100% efficient engine. But this is not possible as per Kelvin-Planck statement. In the second figure, you can see this is again hot reservoir at temperature Th and this is cold reservoir at temperature Tc. And the heat Qc is being transferred from cold reservoir to hot reservoir without any work. Here it is shown that W is 0 and this will give you a workless refrigerator, but this is not possible as per Clausius statement. So this two figure represents Kelvin-Planck statement as well as Clausius statement, or say it represents the second law of thermodynamics. Okay, now let us see next topic, that is 12.12, reversible and irreversible processes. I tell you, you might have never think about reversible and irreversible process from the thermodynamic point of view. So let us see that here. A process in which the system and the surrounding can be restored to its initial state from the final state without doing any thermodynamic changes in universe is called as reversible process. Means a process in which you pass from initial point to final point and you come back from final point to initial point, but in this process you are not doing any change in universe, then it is called as reversible process. Let me explain you with one figure here. This is a P versus V graph and let us take a gas system. Okay, a gas system. This is the initial condition of the gas system. Here the pressure is P1, volume is V1 and the temperature is T1. This gas passes through some thermodynamic process. So it moves from I to F, from initial to final. This is the final point where the pressure is P2, volume is V2 and temperature is T2. Obviously, while moving from I to F, the gas might have passed through many intermediate thermodynamic processes. That's very obvious that it might have passed through many intermediate thermodynamic processes. Now, if this gas can move back from F to I, passing through the same thermodynamic processes, then we can call it that it is a reversible process. But it's very obvious that it will not move from that path, it will rather move from this path. Because while moving from I to F on this path, the gas must have absorbed some heat and it might have done some work W. So, when we say to move back from F to I on the same path, means that the gas must have get the work back and should produce the heat again, which is not possible. So, gas will travel on this path and will reach back from F to I. Definitely, this becomes a cyclic process, but it is not a reversible process, because in this whole cyclic process, the system might have absorbed some heat and might have done some work. That's why this is not a reversible process. Also note that because it's a reversible process, so the thermodynamic system is coming back to its initial position. That's why it is coming back to its initial temperature as well. So the total change of internal energy delta U will become 0. Alright. Now let us move forward. In practice, most processes is not reversible. In fact, all spontaneous process in nature is irreversible. Now let us see some examples of irreversible processes. In this first example, this is a container having adiabatic wall, and here is a stone which is having high temperature, here is an ice cube and air. So obviously after some time this ice will melt and will be converted into water. Now this process cannot be reversed back by its own because the walls are adiabatic. One more example, example 2. This is a container and which is filled with some gas, and here is another container which is empty, and here is a valve in between them. So when I release the valve, means let the gas pass through first container to second container, obviously the gas will pass like this and both the container will have same pressure now. Now this process cannot be reversed back, means it is not possible by itself that all the gas from the second container will be again compressed in the first container. That is not going to happen. So this is not a reversible process. Now example 3. Here is a hot cube, some metal cube, and it is hot right now and it is kept somewhere in atmosphere. So obviously gradually it will cool down and will become a cold piece. Now this process cannot be reversed back, means the object which is cold right now cannot become hot again by absorbing heat from the atmosphere. So this process is not reversible. Example 4. Here this is a container which is filled with some gas at high pressure, let us say, and now the gas is released. So after some time all the gas will be released in the surrounding, which is very obvious, but now this process cannot be reversed back. That means the gas in the room now cannot filled back in this container by itself. So this process is also irreversible. Alright, there are many such examples which we see in day-to-day life. Those are irreversible. Just for example, a combustion of any fuel is a irreversible process. Likewise, conversion of work to internal energy is also irreversible. Means from internal energy we cannot get the work back. So that is also irreversible process. Now let us see why irreversibility arises at all. Irreversibility arises due to two main reasons. The first one is many processes take the system to non-equilibrium states from which the system cannot come back to equilibrium by itself. For example, if we discuss about leaking of gas from a gas cylinder, then here what is happening that the gas initially in the cylinder was in equilibrium state. Now because it is leaking, so it is coming in a non-equilibrium state. So obviously it cannot come back from non-equilibrium state to equilibrium state. And the another reason is the energy loss due to the dissipative effects like friction, viscosity, etc. cannot be reversed back. See, whatever energy is dissipated due to friction or due to viscosity or such type of dissipative effects, that energy cannot be reversed back. And that's why the whole process becomes irreversible. Now, the question is that by any means, can we make a reversible process? Let's see. Reversible process is an idealized notion only. It's not practically possible. It's an idealized notion. But a process can be reversible only if it is a quasi-static and there are no dissipative effects. Remember this thing? If the process is quasi-static and there are no dissipative effects, means there is no dissipation of energy by friction, viscosity and so on, then we can say the process will be reversible. Let us take one example also. For example, a quasi-static isothermal expansion of an ideal gas in a piston cylinder arrangement with zero friction is reversible. See, if we take an isothermal expansion of ideal gas in a quasi-static manner with having zero friction in the piston cylinder arrangement, then it will be reversible. Remember this, isothermal expansion in a quasi-static manner for ideal gas with zero friction can be considered as reversible. Again here I will add that this is also a idealized notion, because when we say quasi-static process, then quasi-static process ideally require infinite time. So this process is infinitely slow. That's why practically it is not exactly possible. Then too, if we assume that the process is quasi-static and it's an isothermal expansion of ideal gas and there is no friction between piston and cylinder, then this process is reversible. That means here the gas will return back to its initial position from the final position, passing through the same intermediate processes which it has passed while coming from initial to final. So it becomes a reversible process. Alright. So students, I complete this lecture here, and as I always tell you, the PDF link of the writing work of this lecture is given in the description box. You can download that PDF and can write down the whole lecture from it. So herewith I am signing off, Anshun Baldania.